welcome. In this video, we're going to discuss another way to estimate our statistical parameters. In previous videos, we've talked about the MOM, method of moments, MOM estimator, as well as the MLE, more popular MLE, maximum likelihood estimator. Both of these are given real-life data, which is generated from some distribution with an unknown parameter, trying to use that data to estimate what the actual underlying parameter is. So we're going to talk about Bayesian estimation and posteriors and priors in this episode, or not episode, because it's technically an episode, but in this video. So let's say we observe data that we're going to label x1, x2, all the way to xn. Let's say that each of these x's are identical, independently distributed, Bernoulli p. So, I think in the, I should also mention the book that kind of discusses this and the chapter that talks about this specifically is linked, so you can read along. This is just kind of redoing it in video version, sometimes easier to understand. You could think of, in the book, I think we said xi is the indicator random variable that a random person has seen Lord of the Rings. So xi is 1 if a random person you go up to has seen it, and 0 if they haven't seen it. And we are looking for p, which essentially is the probability that a random person has seen Lord of the Rings. So we observe our data. Maybe we observe that 60% of people have seen it in a sample of 20, and we want to see what that tells us about p, our true parameter. Again, in probability, we are given the p, and then we think about the probability of different stuff occurring with the data. In inference, we're given the data and seeing what inferences we can make about p, the parameter. So we're going to start with what's called a prior. With maximum likelihood, we kind of did something different. In Bayesian estimation, we're going to start with something called a prior. That's saying that p, we're going to say p, our true parameter, we're going to assign it a distribution. In this case, we're going to assign it a beta distribution with parameters a and b. I'm just going to use a and b generally. They can kind of, be anything you want. And I'm just going to write prior here. Basically, what this is doing is saying, okay, I'm not really sure what p is, so we're going to say it has some distribution, and I need to pick a distribution that makes sense. A beta makes sense because a beta support is from 0 to 1, and probability is from 0 to 1, so this kind of makes sense. The other thing that makes sense is a beta 0, 1. Oh, actually, we'll get to that soon. Don't want to spoil anything. This is the PDF, the density, probability density of p with this distribution. So we basically have p to a minus 1, 1 minus p to b minus 1, and then this, it looks weird, but it's a constant. Don't be scared by these like crane things. It's just a gamma function, and it's a nice way of writing n minus 1 factorial. So anytime you see a crane in there, it's just the value minus 1 factorial. So don't worry too much about that. Okay, so we now, the whole point of this problem is to try to learn more about p. And we have a prior distribution for p. Going into it, we have kind of, what we think about p. Maybe our distribution looks like this. We're not that sure. We have a slight inclination that it's up here, but we're not super sure. Maybe it looks totally flat. Maybe we have no idea where it is from 0 to 1. This is called an Uninformative Prior. It's a uniform 0 to 1. So we want to learn more about p by observing the data. The way we do that is we say, what's the distribution of p conditioned on the data? Okay, conditioned on the data. And for this section, I'm going to, just to make things a little cleaner, we're going to say x1 plus, what can I write this? I'll write it here, sure. We're going to say x1 plus x2 plus ... xn. We're going to say that equals x. We're just going to call that x. So the sum of all the x's is x. And that has a distribution binomial NP by definition, because it's the sum of n independent Bernoullis. So now we are curious about the distribution of p conditioned on the data we saw. So we observed some data. What's the distribution of p? And this equals, by Bayes' rule, which you remember from probability, the distribution of the PDF of x given p. In this case, it's a PMF because x is discrete, times prior of p all over the PMF of x. Okay, this is just Bayes' rule. You can think of it, usually we write this with probabilities. Now we're writing it with probability density functions. It's the same kind of gist. One thing is that we are interested in the distribution of p, right, conditioned on x. So we only care about terms that include p. That means that we actually don't care about this f of x term. This f of x term is a PDF that just has terms with x in it. It doesn't have p in it. So we actually don't need to know that. So we can erase it and we can write proportional to, which is that little sign that looks kind of like a fish. And that's a little bit weird. It takes people kind of a while to get comfortable with that. But remember that, you can look at the PDF of P, the prior of P. We have this term here, and then we have a P term and a P term. This term is kind of just a constant. So when you do all the calculation out, it's going to come out to a number, 0.7 or 0.25. So it's 0.25 times a function of P, times something that changes with P. So our answer is going to be proportional to this p term, and we'll just multiply it by some constant. So we don't really worry about the constant. And now we can plug in, right? Now we can say, okay, what's the distribution of x given p? Well, the distribution of x is binomial given p. What's the PMF of that? We can write that down and choose x, px, minus p, x, right? We don't care about terms that don't have p. This term has p, this term has p, this term does not. So I can erase that and write proportional to times the PDF of p. And again, we don't care about terms that don't have p. So I'm going to look at this thing and just write the terms that have p. Can you see that? Yeah. Now we're going to add or combine terms. So we add in the numerators in the exponent. So p to the x, p to the a minus 1, p to the a plus x minus 1, and then 1 minus p to the x, 1 minus p, b minus 1, 1 minus p to the, I'm sorry. So I messed this up. You're probably yelling at your screen. This is n minus x, right? We have x successes, n minus x failures, and I have this n choose x in here because that's the number of ways to choose x successes out of n trials. I should have stopped to explain that, sorry. So probability p of success, x successes, 1 minus p failures, n minus x failures. So then we combine these two terms, n minus x plus b minus 1. And all of a sudden, what does this look like? This looks like the part of a beta. This looks like the part of a PDF of a beta without the whole gamma normalizing constant thing. In fact, this looks like px is beta, and you can kind of sort of pattern match, right? You have beta AB, and you can see where the A's and the B's go. This thing is a PDF of a beta, a plus x, n minus x plus b. Okay. And let's think about this intuitively. X, little x is the number of successes we observed. So a plus the, this first, the value is, the first parameter is the number of a plus the number of successes. The second is b plus the number of failures. So what happens is we now have a new distribution for p. You can see that it updates with x. As we collect data, the distribution for p will change. And what is that distribution going to look like? Well, let's say that, let's start with a totally uniform prior, okay? Let's say we observe a bunch of data, we observe a bunch of x values. And let's say we get 10 successes and 2 failures. So, or, we get enough successes such that a plus x is 10 and enough, so we can start with beta of 1, 1, and then we move to, we get 9 successes and we get 1 failure. Basically, the idea is, let's say we get more successes than failures. The beta is going to look like this. And I didn't really draw that perfectly, but you kind of get the idea. If the a parameter is very large compared to the b parameter, the density of the beta is moved up closer to 1. We get the opposite if we have like a beta 315. If we have b, the b parameter is much bigger than the a parameter, then the density of the beta, so the probability of the beta is all, humped up next to closer to 0. So the idea here is that p conditioned on x, if we see a bunch of successes, and this parameter is larger than this parameter, so more successes than failures, the distribution of p, like our estimate for p, is going to move higher, closer to the right. Because if we observe more successes than failures, we think that p is greater than 1/2, it's closer to 1. If we see way more failures than successes, so this term is bigger than this term, we get something like this, where our distributional estimate for p is much lower, right? It's below. We only observe 1 success and 10 failures. We think that p is pretty small. The probability of success is pretty small. And what's cool here is, like, let's imagine if we really upped the ante and saw this was 100, to 2. The distribution not just moves, close to the right, but it becomes very, very narrow around, some mean. So the more, the more trials we see, the more, stuff that happens, we get higher and higher conviction. We get a tighter and tighter distribution. You can automatically start to think about confidence intervals, right? Like, what's the middle 95th percent of this distribution? I'm 95% sure that p is within, the true proportion is within that. You thought a lot about proportions probably in a very, cookie cutter kind of formulaic sense. Here we have a live breathing distribution for p, and we can just chop off chopping off is bad to say when I'm saying it's alive and breathing. We can just consider the middle 95%. So maybe this is the 5th percentile, maybe this is the 95th percentile, and everything in the middle, we're 95% sure. This is really the 2.5 and the 97.5. And 95% in the middle is, we're 95% confident that p is there. So again, you see a lot of successes relative to failures. You're going to get p, the distribution of p, kind of crowded up on the right. You see more failures relative to successes. The distribution of p moves to the left. The bigger one of these gets relative to the other, the more confidence and the tighter the distribution for p is going to be. The last cool thing to note is that we saw that we used we used a beta for a prior for p. We saw why that was good. It's between 0 and 1. We can fiddle with a and b to kind of shape the prior how we like. We used this as a prior. Then we had a binomial setting for the data. And the posterior distribution we got was beta. So we started with a beta, ended with a beta. That's something called a conjugate prior. When the prior ends up being, in this case the beta is the conjugate prior, the prior ends up being the same distribution as the posterior. That's really nice because you can see we have beta, we update, we observe some data, and we still have a beta. So you can continue to update and observe more data, and we still have a beta. And we just have this really nice distribution for p, this beta distribution. And we can kind of just use that to inform our estimates about p. So this is a really, I think, slick way of doing estimates, and it's a cool Bayesian approach. Works really well with this binomial beta case, but there are tons of other examples about how you can use priors and posteriors to find estimates for parameters that you want to know more about. So we'll see you next time.